I'd like to welcome everyone. My name is Andy Aquila. I'm the one who's setting up these talks. This is the Applied Science Technology talk. This is the second year we've been having it. This year, and actually this semester, we're very lucky. We have some really great talks. We are covering everything from the ultra-large of Jupiter to the ultra-small of Nano, and virtually everything in between, including biofuels. So without any further ado, for those of you in AS&T, you probably have all at least met Professor Marcus. If not, he at least is the one who signs your paychecks, being the head graduate advisor. So he's also the only mechanical engineer I know who ever works on astrophysics. And and because of this, he matches so well to our program, which is very interdisciplinary. So without any further ado, Professor Phil Marcus.
Thanks. And sign your paychecks. Okay, so what I want to talk about today is sort of a follow-up of some research that I did about 5 or 6 years ago. And I want to talk about Jupiter in terms of climate change. I should say that my collaborators here, the person who probably did most work on this is an AS&T student, Zyler Assay Davis, whom I think most of you know. And I've got collaborators from astronomy as well. And here is a great red spot, and over here is a new red spot, and that's really what I want to talk about today, because I think it is. Is my microphone on? It says it's on. It's on. Okay, good. Can you not hear me? All shallow. Okay. Okay. So what I want to talk about is Jupiter's undergoing a major upheaval. A climate cycle or climate change. This picture was taken about 9 years ago of Jupiter. Look at the equatorial regions. This is the red spot. But the equatorial regions, you see a nice white band across it, an orange band, straight lines. Today, what Jupiter looks like in the equatorial regions is quite different. You see these very large, is there a laser pointer here, by the way? Or something mechanical? All right, fine. You can see at the top of my shadow there, you can see these disturbances here. These are not nanoscale disturbances. These things are, the whole planet's diameter is about 140,000 kilometers here. These things are a good chunk of the size of the planet. So the United States or North American continent would fit into those many times. So there's these white, large structures here. There's this intrusion of what was formerly a nice parallel line separating the orange and the white. There's a lot of disturbances happening right now on Jupiter. Here is this new red storm, this red oval or red spot. And the actual great red spot hasn't disappeared. It's simply on the other side of the planet when this picture was taken. This is a dynamic picture created by Zyler of the red oval. You can see it goes around. It's a vortex. It is an anticyclone, which means it's rotating in the opposite direction of the planet. So it is moving in a counterclockwise direction here. Okay. So when I talk about climate change on Jupiter, I've got to sort of go back and say what I mean. We started publishing rather controversial papers in around 2001 when we made a prediction that there would be a significant climate change on Jupiter starting in around 2000, well, starting in 2001, but with observable consequences beginning in around 2006. This new red storm appeared in December 2005. We also predicted that the change would occur from just north of the equator to about 34 degrees south. The new storm is at 34 degrees south. So it may be a coincidence, but on the other hand, Jupiter cooperated at least with our papers in that it made a change at the right time and the right place. So for that, I thank Jupiter. All right, so a change from what? You have to say what was there before. So our general picture of Jupiter as well as the other major outer planets came from the Voyager flyby, which went by Jupiter in 1979. And it made very striking color pictures that were in all the news media, basically not contradicting what was observed from ground telescopes, but really sort of giving us a picture that the planet consisted of stripes and spots, or jet streams rather than stripes, and vortices rather than spots, as well as some turbulence. So unlike Earth, which has two major eastward-going jet streams. Jupiter has 12. It also has 12 westward-going jet streams. The characteristic velocities are anywhere from 50 to 100 meters per second in these. And superposed on these are long-lived vortices, the most famous of which is the Great Red Spot. Several vortices have been documented for a long time. You can tell when something's been documented and has fallen into the fashion of being considered a more or less permanent feature. It's given a name. So along with the red spot, there were 3 white ovals. 90% of the vortices that were identified from Voyager that were considered long-lasting were anticyclonic. That was, they were in a counterclockwise direction rotating, at least in the southern hemisphere. And there really weren't many considered documentations of the cyclones. And the characteristic velocity of the turbulence is only a couple % of the characteristic velocities of the vortices and of the jet stream. So that was the picture that we had. Here is a physical picture that was published in Icarus by Sanjay Lemay. So superposed on top of a cylindrical projection of the clouds is this magenta line. The magenta line shows the average east-west winds. So every time you see a peak over here, it's one of our eastward-going jet streams. And every time you see a peak in the other direction, it's a westward-going jet streams. So the entire planet is sort of littered and covered with these jet streams. And as you can see from the picture, on top of it are, at least from the implication of the clouds, a bunch of vortices. So here you see a great red spot. Let's see. So the characteristic thing then that was seen was that, except for the red spot, their belts and zones, those stripes, are filled with rows of anticyclones. The anticyclonic vortices aren't just randomly placed throughout the planet. They occur in rows, that is, rows of constant latitude. And each latitude has, where there's a westward jet stream, you're going to see just on the poleward side of that rows of these anticyclonic storms. So that was the picture of Jupiter. So here you have another one. I apologize, the projector seems to wash out the red color, which is an important thing to wash out if you're talking about new red spots. This almost looks black and white. But here you see a row of vortices going off on an angle. It's at an angle because the projection here. Here's a cylindrical view taken of the planet. Here you see a great red spot. But here you see a latitude that has lots and lots of white, bright, elliptically shaped vortices. You can see them at 41 degrees south here as well. But the entire planet is littered with these vortices. And we started analyzing, or rather my graduate students started analyzing what would allow not just vortices to exist, but why should they appear in rows, and why would those rows be stable features? And it is more or less explained by the top cartoon there in the upper left, where you see the parallel arrows represent the fact that these vortices are all embedded in shearing flows. So to the top or north of that is an arrow representing a westward-going jet stream, and below that is an eastward-going jet stream. And inside it, you see the vortices going around in a counterclockwise direction. They're labeled A's because they're anticyclones. Vortices just go with the flow. They generate their own flow, so each vortex produces its own counterclockwise rotation around it. So they feel those rotations, and they also feel the velocities of the jet streams. So even if you could have you could have an equilibrium configuration, if those two vortices labeled A1 and A2 had exactly the same strength and were located at the exact same latitude, but even the smallest perturbation that changes their latitude, say that moves A2 up and A1 down, then they're no longer feeling the same east-west velocities, and A2 will approach A1, A1 will approach A2. And when you have two vortices that rotate in the same direction, we know from lots of numerical experiments and lab studies that they quickly merge together. So if you had just a row of anticyclones, it wouldn't last very long. It tops a few months on Jupiter. And so the way we were to stabilize that, so if you put a row of anticyclones and offset from them is a row of cyclones, vortices moving, rotating in the other direction, that's a stable configuration. So here we have a picture over here on this right side. It's a cartoon of what the east-west velocities look like. So here's a westward jet stream. Here's an eastward jet stream. Here's another eastward jet stream. The westward jet stream has the cyclones on the equatorial side and the anticyclones on the poleward side. So this is a view of the southern hemisphere. And this is a very stable configuration known as a Kármán vortex street, because I could put an equilibrium row of vortices here and kick this guy A2 up. So we can add a small perturbation and see what happens. Well, if we move him upward, he feels the velocity of the westward going jet stream more intensely, and so he will move to the left. But before he becomes under the influence of his neighboring anticyclone, he'll come under the influence of the cyclone in between. The cyclone's producing velocities in a clockwise direction. He feels a downward flow here, and so he's pushed downward. When he gets downward, he comes on more to the influence of the eastward going jet stream. And so he not only returns to his original position, he actually goes in an east-west kind of very elongated orbit. And you can calculate those. In fact, those orbits were calculated approximately 100 years ago by some of the earliest fluid dynamicists who looked at phenomena where they saw rows of vortices in the lab, these Kármán vortex streets, and treating these as delta functions, you can work out the stability of those rows, and then you can calculate what the eigenmodes are. And the eigenmodes, indeed, were these east-west oscillations. These guys are repelled by their neighboring cyclones, just as the way the cyclones won't get near each other because they're repelled by an intervening anticyclone. So it turns out that we believe now that all of the rows of vortices on Jupiter, even though the cyclones are very difficult to observe, are actually staggered in this particular configuration of oscillating vortices. So here again is why these guys repel each other. They're self-repelling. If I've got my westward jet stream there and eastward jet streams at the top and bottom, if these guys try to get close to each other, the way their velocities are set up, they'll both move each other northward. Moving the anticyclone northward brings him to the left. Moving the cyclone northward will bring him under the influence of the eastward jet stream and to the right. So it's a nice natural repelling mechanism. It also explains why there's just one great red spot. Jupiter has a very stratified atmosphere, meaning it's difficult to penetrate vertically. So the vertical velocities on Jupiter are very small. You've seen that in our own atmosphere on Earth. It's very difficult to get large vertical velocities. We're used to large horizontal velocities, but normally you don't get a weather forecast saying the upwelling winds going straight up are going to be 30 miles per hour this afternoon. Don't bring an umbrella. And the reason for that is because it takes a lot of energy. The atmosphere is very stably stratified, meaning if you were to take a parcel of fluid from the bottom and try and move it upward, you'd have to pay a tremendous amount of energy to do that, because you're lifting up fluid that would be heavier than the ambient fluid. And you see that, for example, even when you have big energy perturbations, like you do atmospheric testing of nuclear weapons. In the atmosphere, you don't get, you produce a ball initially where of superheated gas where the explosion occurs of a few thousand degrees, and it starts to rise because it's buoyant, but it doesn't get very far. It gets up into the atmosphere, it becomes stably stratified. Instead of going up, it goes out and gives you the classical mushroom cloud. So in Jupiter's atmosphere, which is stably stratified, and it's a rapidly rotating planet, those two things together tend to make the velocity field not up and down, but two-dimensional, mostly east, west, and north-south velocities. Vortices only form and are stable for more than a few turnaround times in a turbulent atmosphere or turbulent environment if they're two-dimensional. At the equator, Jupiter is not very two-dimensional. It's rather three-dimensional. You can see that in direct observations where you can see clouds forming due to vertical velocity components. And also the effect of Coriolis force, which makes it 2D. Coriolis force is one sun in the northern hemisphere and one sign, different sign in the southern hemisphere. So at the equator, it's 0. So the equator is a rather unusual place and rather 3D. So you don't see near Jupiter, on Jupiter, you don't see any long-lived vortices within about 20 degrees, 15 degrees of the equator. So if I have in the schematic a bunch of vortices, these anticyclonic things going in the counterclockwise direction, to preserve them as multiples, if I need intervening vortices of the opposite sign, I can do that at most latitudes, but I can't do it near the equator. The great red spot is about 23 degrees south of the equator. If I had multiple red spots at that latitude, I would require having long-lived vortices of the opposite direction within about 15 degrees of the equator. I can't do that because I get no vortices that are long-lived because of the three-dimensional motions at the equator, and therefore I can only have one great red spot at its latitude, not multiple spots which you see at other latitudes. So publishing a paper, of course, on this in 1993, where I said that not only don't the vortices, the anticyclones, merge together, they're never going to get near each other because they're going to be repelled by the intervening cyclone. The bad news, good news was about 5 years later, when we looked at the vortices just south of this equator, this row around 34 degrees, and these are two anticyclones. They're called white ovals. There are 3 of them at this latitude. This is a cyclone. It appears very clear in this picture because the influence of these two anticyclones is making the cloud structure of the cyclone very bright and prominent here. And these guys travel together, apparently not repelling each other for several years. And so this completely says what we published in 1993 was wrong, or perhaps not the complete story. So let me try and give you what the complete story and where that went. So just in the southern hemisphere, south of all those anticyclones, the red spot, here's a white oval, is a westward jet stream. Westward jet streams represent discontinuities typically, eastward jet streams. Those represent discontinuities in vorticity, and waves are allowed to propagate along those called Rossby waves. And they're a phenomenon not only seen on Jupiter, but on Earth as well. And waves have peaks, and they crests, and they have troughs. And things can get trapped in the trough. So last time I gave this talk was Monday, October 8th, 2007. And I illustrated the talk with this picture stolen from the Weather Channel. It was the day's weather. Here you see our one and only in the northeastward going jet stream here. And here you see a cyclone there. And that kink is a Rossby wave. It's the trough of a Rossby wave. And this unfortunate cyclone has gotten trapped in the trough of this Rossby wave. And in fact, if you look at most days' weather patterns, you'll see the undulations on the jet stream. Those are Rossby waves. And more often than not, you'll see a storm, either a cyclone or an anticyclone, trapped in the kink there, or the trough of that wave. Well, the same thing can happen in the laboratory and on Jupiter. So here, schematically, is an eastward going jet stream. And here's an anticyclone, and it is happily trapped in that trough there. Well, what one of my former students, Ashraf Yosef, discovered and worked on in his PhD thesis is that you can have any odd number of vortices that make up a Kármán vortex street trapped in the trough of a Rossby wave, and they will stay together like this. These shoulders of the Rossby wave are concentrations, respectively, of cyclonic vorticity, and so it's like having two virtual cyclones on either side to shepherd this into a nice packet. And what Ashraf found was, if you had a configuration like this, there's a critical amplitude of the cyclone that if you make it big enough, the repelling factor becomes big enough to overcome the shoulders, and this group of 3 vortices will escape from its trough. Similarly, he found that if you had these vortices free in a Kármán vortex street happily oscillating back and forth, there was a critical amplitude of the cyclone. If it became weak enough, that is, not repelling enough, this group of 3 would fall in and get trapped by the trough. So he looked at these ideas and tried to see if he could do numerical simulations using values that corresponded to our best estimates for what these vortices and jet streams looked like for Jupiter. So here, and I apologize now for the granulation of the simulation because it's just one little tiny corner because we were doing a great deal of Jupiter in our simulations. Here are two anticyclones indicated by red. Here is a blue cyclone in between it indicated by blue. And we wanted to show there was a repelling factor here. So these guys are embedded in jet streams. You can't see the jet streams here, but we made no jumps in vorticity at the jet streams for this calculation, so no waves could be produced, no troughs or crests could be produced to do any trapping. And so in order to see this a little better, I'm going to stretch this out in the north-south direction. And then as a movie, you can see that this does have a repelling action. The two red vortices, even though they're in a shearing flow, don't get together. They're repelled by the little blue guy in between. And you can see he's oscillating back and forth. And if I had another little blue guy over here, he'd push this red guy back. And I could have, say, 3 blue and 3 red. If I had that, that would correspond to the situation of Jupiter before 1996, when there were 3 red-colored, not red-colored, white-colored, but anticyclones with 3 cyclones repelling them in between. And you saw oscillations, and those oscillations in longitude were recorded dutifully by mostly amateur astronomers for almost 70 years. So then Ashraf repeated the exact same calculation. The color here represents something called the potential vorticity. But let's just say that the jet stream now that goes to the east is highlighted by the color from light blue to dark blue, because we're allowing it. The velocities are exactly the same as they were in the last movie, but here there's a jump in the vorticity which allows waves. And now you can see what happens, and this is what we think happened after about 1996, was that 2 red guys, right, have a blue guy in between, and he's going back and forth, sort of ping-pong diplomacy between them. But the shoulders of this wave, which you can see are blue like the cyclone, they're squeezing these guys together. And this will travel as a unit like this, basically indefinitely in this calculation. However, there's one slight thing that I didn't tell you. If for some reason there were perturbation to kick out that blue guy and these 2 reddish-orange guys were next to each other, then they would merge almost instantly. Without this jet stream, this blue, light blue discontinuity there, in order to shift the positions of the pattern so that there's 2 red or orange guys next to each other and then 2 blue guys next to each other, requires a huge perturbation. On Jupiter, putting in the actual values, we looked at that. You'd have to whack the system with something that had about 30 meters per second perturbation to get the longitudinal ordering of those vortices to change. And that's just simply not available on Jupiter, right? The turbulence is about 2 meters per second. On the other hand, when you have this situation of 3 vortices here all chopped in a trough, the sides of this trough are squeezing this thing together really badly. They want to squeeze out that blue guy. And just playing with this, we discovered that instead of needing 30 meters per second perturbation, you needed about 1.5 meters per second perturbation to get this thing to be unstable to kick out the blue. So here's a picture at the top that was captured from that last movie. Here was a picture that was taken by one of our spacecraft that appeared above the fold in the New York Times. And this is a cyclone. These are 2 anticyclones. And I think there is some similarity there. It's a qualitative description, I think, of what's going on. It's pretty good. OK, so this was then the history of these 3 white ovals, which were given names because they were anticyclones. The cyclones in between, which are hard to observe, were not given names. But you can see a little black region there and a little light region there. Those are the cyclones. So in September of '97, the 3 white ovals, which were given the romantic names of FA, DE, and BC, were there, and they were distinct objects. By July '98, there had been, one of them had disappeared. It was not seen disappearing, but my conjecture is, Ashraf's conjecture was that 2 of these guys merged together. like that's generally accepted by the community. By September 2000, all three of the vortices had merged together. And we take one letter from the guy on the right and one letter from the guy on the left, and we've got a new white vortex given BA. So that's kind of the history. So now, if we understand perhaps why these guys bunched up, what caused them to merge, and the idea is that between these guys, there's a westward going jet stream, and all I got to do is kick out by some mechanism the cyclone, and then I've got two anticyclones together, and they will merge very quickly. So the repelling mechanism is still there, but if we get the cyclone out, we don't have anybody to repel. All right, so here is the picture we had before the merger. And so here now is a movie. So what we did was exact same movie as before, except we put another little cyclone over there, a blue guy, just to come in and do a little perturbation. Probably what happened for the mergers in reality on Jupiter was they were perturbed. This little basket of three vortices was perturbed as it swept just south of the Great Red Spot. Doesn't really matter. Any perturbing thing is going to have consequences. So here we see the movie here. We see these three guys trapped nice and close together. And then this blue guy is going to come in, and he'll be repelled. You'll see him come in and shift to the right. But he imparts a little bit of a perturbation to the vortices, and the blue guy is ejected, and the two red guys or orange guys merge together. And we think then that's how the vortices all merge. So the question is, what does this have to do with predicted climate change on Jupiter? And the answer lies in this figure over here, where I've got the latitude, so the poles are a little bit off the ends of this. Here's our equator. Jupiter has a heat source of its own. It also absorbs energy from the sunlight, about twice as much as absorbed from the sun as its own internal heat source is. The line to look at here is the one at the top, which is basically the net thermal emission from the layer that contains the clouds, right? That's the layer that contains the clouds that you and I see when we look at Jupiter. That's where we deduce all of our wind velocities. So that layer is happily emitting off thermal radiation, and there is not much variation between the poles and the equator. And so the question is why on Earth, which is just like Jupiter gets more heating at the equator than it does at the pole, we expect and we get the fact that the equator is warmer than the poles. So why isn't that true on Jupiter? There must be something doing meridional heat transfer there. So there's a heat transfer problem. The cloud layer is clearly, Jupiter has a convective zone below the cloud layer. They are clearly disconnected from each other because I couldn't have a three-dimensional convective zone and have vortices happily doing their oscillating thing. It's just incompatible. So the bottoms of the vortices are probably well clear of the top of the convective zone. All right. The radiative transfer experts in the field think that at least half of the energy that is absorbed from the sun is absorbed directly into the weather layer. If it were absorbed completely into the convective zone, which mixes everything up, down, sideways, you would have no problem explaining why the equator and the poles were the same temperature. But because it's absorbed in a layer of clouds that is well clear of the convective zone, there must be some mechanism that is in that convective zone itself that does the transport. In fact, you could crudely model the system of clouds and say, let's let the bottom of that be the convective zone, and let's put in a thermal boundary condition at the bottom that allows no temperature gradients at the bottom of the weather layer between the pole and the equator. Even if you took that severe condition that that's what the effect of the convective zone was doing, you would still have about a 30-degree difference between the poles and the equator on Jupiter, and you don't have it. So something must be doing the dynamical mixing. All right, let's skip that one here. OK, so one explanation of what might be doing it is we know that chaos is very, very good at mixing just about anything. So if you're a painter and you want to make pink paint and you pour white paint and red paint into a bucket and you stir, it's extremely difficult to get good mixing and create pink paint, even if you fairly vigorously stir. But if you're chaotic in the way that you stir, then you get very good mixing. So the subject of chaotic mixing has been around for at least 15 years and described in detail. There are papers, books, treatises on it. And we know that chaos is very good at mixing things whereas if you do things in a non-chaotic laminar way, even with the same amplitudes of velocities, your mixing is quite poor. So there's a question here of maybe chaotic mixing is bringing the heat from the equator to the poles by some mechanism. And one obvious mechanism here is this guy over here. Here are the three white ovals in September 97. They're not just don't only have big velocities of order 100 meters per second, they're going back and forth just like a painter would want them to do, to mix things up in a very chaotic manner. Okay, so a very crude simulation of Jupiter with three chaotically oscillating vortices mixes the heat between the pole and the equator just fine. It's completely consistent with the observations. Even two vortices bouncing around with turbulence will do that. But if you only have one vortex, your chaos disappears, and the calculation shows that you don't have good mixing anymore. So we therefore, or with my student Ashraf Yosef, decided that, gee, maybe the vortices of Jupiter are more than just decoration. Maybe they have an important dynamical influence on the atmosphere of causing the meridional efficient transport of heat, and they're therefore responsible for making the poles the same temperature as the equator. If that were true, then if you suddenly killed the heat transfer mechanism at 34 degrees south latitude, you would expect the equatorial regions to get warmer because you've blocked the heat transport, and you would expect the polar regions, or regions south of 34 degrees south latitude, to get cooler, and that might have some dynamical consequences. Some of those consequences might be, for example, the following. You might see that if you look at the the eastward and westward jet streams on Jupiter, they may be stable with respect to convection, but they are not very stable with respect to baroclinic type instabilities, which is a combination of convection and rotation, and in this case stratification of the atmosphere. And if you started changing temperatures, you might make those go unstable. You might see those would be characterized by waves on those jet streams that when they become unstable, if they really became quite nonlinear, the waves would break, roll up, and probably produce new vortices. So we expected there might be some consequences of some dynamical importance that even amateur astronomers might observe. It is extremely difficult to either support or refute this idea that there might be changes in the temperature due to the meridional heat transport blocking, because we don't really, Voyager spacecraft happened to have in place the instruments that we needed to really understand what the average temperatures were on the planet. We don't have an instrument in place today that can easily do that. So any subtle changes of a few degrees in temperature would not come up immediately in any of our spacecraft observations by direct measurements. When might these effects be observable? Well, if the heat shutdown started in the late 1990s, the characteristic thermal time scale of the atmosphere, its thermal radiative relaxation time, at the level of the clouds is on the order of 4 or 5 years. So we might start seeing effects in around 2005, 2006. So that was what we had published in our articles, including our Nature article in 2004. So are there any effects of that? Well, as I began this talk, I said that Jupiter's got a new red spot, and other things are happening. So the question is that what might be expected by a temperature change? Or is there some other plausible explanation of the red spot? So the new red spot wasn't or this red oval that's at 34 degrees wasn't a whole brand new vortex. It was when these three guys merged together, they made a vortex which we called BA. When it formed in around 2000, it was bright white. But in 2005, late 2005, it turned to the same kind of brick red color as the Great Red Spot. So it wasn't creating a new vortex. It was simply seeing a color change. In the 350-odd years that Jupiter has been observed since Hooke and then Galileo looked at it through the first primitive telescopes, We have never seen a large vortex change from white to red before. It's a totally new phenomenon. There have been little blips of transient red vortices, but this is something new altogether. So the question is that a coincidence? Is it have something to do with temperature change or what? So let me say two things. It's not just, and I apologize again that on my screen this looks very red. On your screen it looks very dark. This is a vortex. It's got a white core. The red, unlike the great red spot, is not everywhere. It's confined to a ring on the outside of the vortex, still inside the vortex, but right at its outer boundary. Inside that ring and outside that angular ring, it is not red. And so that's a fact that's very, very important, I believe, as is the fact that this vortex was created by a rather cataclysmic collision of vortices. Remember, these things are big. They're 13,000 kilometers in the east-west direction. They're big objects. It didn't suddenly turn red at that time. It turned red about one thermal time scale later. So the question is, can we use those two facts to shoot down many of the other possible explanations of why it turned red and say why this might be an indicator, a thermometer, if you will, of a temperature change on the planet? So that's what I want to spend the last few slides talking about. So this is a picture that was created by the group of people that you saw on the first slide. And it is the velocity of the red oval. So in fact, it's two velocities. So what we've done here is we've taken a slice through the principal axis, through the diameter, the east-west diameter, and that's what's along this axis over here. And what we've plotted here is the north-south velocity along that diameter, except we've done it twice. We've taken Cassini data. So Cassini did a flyby mission. Cassini was a mission that took data in 2000, and that is shown by the broken line here. And we took our own Hubble Space Telescope images in the spring of 2006, and that is shown by the solid line here. The scale of the north-south velocities, you can see these are in kilometers per second. So these things are on the order of 100 meters per second. And the uncertainty in the Cassini data is about 3.5 meters per second, about 3%. In the Hubble Space Telescope data, it's about 5%. And there's a whole nother talk involved in getting this figure. This figure, the way people extract velocities from telescopes and satellites is you take two images separated in time by the clouds, and you assume that the clouds go with the flow, and you track where a cloud moved, and you take its length, and you divide by the time, and you get velocity. People did that by hand for the first 20 years of data collection on Jupiter. Now we're using automated methods that are derived from the methods that we use in the laboratory flows, where in a laboratory now you use methods called PIV, particle image velocimetry, or correlation image velocimetry. You put in passive tracers, typically titanium dioxide spheres, and you do a laser sheet illumination, and you watch where they go. And you just don't track them. You do correlations and a lot of statistical analysis. So all that plus much more went into getting this figure over here. So there's a huge amount of work. But what this figure shows is that the peaks are in the same place, and that the velocities are nearly identical. So any argument that says, oh, the red coloring, going from white to red, corresponded to a large change in shape or size or velocity of this vortex, is simply incorrect. Okay, so here, this is direct two-dimensional measurements. We've done simulations and analysis to show that if the two-dimensional velocity that you see by looking at the cloud motions doesn't change, then nothing of the vortex has changed. That you can create from a two-dimensional slice the entire three-dimensional velocity and field and the temperature field and the pressure field within the vortex. Those are unique. So if this doesn't change, nothing changes. And by the way, you can look at this slice not only through the east-west axis of these vortices at two different times, but any angle you want, including the north-south slice. The vortices are basically identical. Now, I said something a little bit too strong. I said from the velocity field, you can infer the temperature, pressure, and density inside the vortex, and that's not quite true. What you get is the anomalous pressure, temperature, and density inside the vortex. And by that I mean the following, that inside that vortex, the vortex on Jupiter is an anticyclone, and like an anticyclone in the Earth's atmosphere, Anticyclones, when you look at the weather map, are indicated by high pressure anomalies. It's a high pressure interior inside that vortex that balances the Coriolis force and gives you an equilibrium. So in the horizontal directions on Jupiter as on Earth, cyclones are low pressures, anticyclones are high pressures. If you tell me the velocity of the azimuthal velocity around this vortex, I'll tell you how big that high pressure is. But we mean high pressure with respect to the surrounding ambient flow. So from this calculation, from this data, you can do the calculation. This doesn't give you the absolute pressure in the center of this vortex. It tells you the relative anomalous overpressure compared with the outside fluid. And from that, you can get the anomalous temperatures and densities as well. So it may be that the absolute temperatures, pressures, and densities in this red oval are different than when they were white, but the anomalous ones are the same. And that's important, because here's a three-dimensional schematic of what we've done. The cloud sheet somewhere in the middle of this vortex is where we see the clouds and get our velocity data in the horizontal direction. Okay. In the center of that is a high-pressure region compared with the outside that keeps things in balance by the Coriolis force being balanced by the pressure gradient. Okay. As you go up and down from that, eventually the velocity in the azimuthal direction is 0. When that happens, we call it the top and bottom of the vortex. So that's what these lids are. The top and bottom of the vortex, the velocity is 0. The pressure at the top and bottom is linearly related to the azimuthal velocity. So if there's no azimuthal velocity, the anomalous pressure is going away at the top and the bottom. However, the top and bottom have anomalous pressure, densities associated with them. In the vertical direction, there's no Coriolis force. Right? If I just had my high pressure center in this vortex, it would be balanced in the horizontal direction by Coriolis, but there's nothing balancing it in the up and down or vertical direction, so it would just blow itself out. Therefore, what balances this vortex is there's an anomalous density at the top and bottom. This lid at the top is denser than the surrounding fluid. This is more buoyant than the surrounding fluid. In the vertical direction, there's a hydrostatic balance between this anomalous pressure gradient and this dense lid and buoyant bottom. So that's how we can estimate and find that there's a dense lid at the top. Moreover, that's not the end of the story. If we have a density anomaly and a pressure anomaly, you can figure out from the ideal gas equations what the temperature anomaly is. And you find that there must be a cold region that corresponds to this dense lid at the center of this vortex. So that's how it keeps its equilibrium. Of course, I said there was a thermal time scale of about 4 or 5 years on this planet. So after this has achieved its equilibrium, that temperature anomaly is going to go away in 4 or 5 years, making the density anomaly go away. And what would happen? Well, you don't have enough of a lid to keep things down, so you'll slowly, along the central axis of this, get rising motion along the upper half and sinking motion along the bottom half because your dense and buoyant lids have gone away. However, that's okay. This is a stable atmosphere, which means when you have rising motions, you cool things off. When you have descending motions, you warm things up. That's adiabatic warming, adiabatic cooling. That's why it's the descending and adiabatic heating of things, for example, that's making the Santa Ana winds right now so devastating and burning down Southern California. As the winds come off of the high plateau, they're descending adiabatically, their pressure is getting bigger, and that means their temperature's got to increase. Same thing's happening here. So along this, let's look at the upper part of this. You've got an ascending motion, horizontal spreading out, and descending motion. And you can numerically calculate this, but you can also do this by a back-of-the-envelope analytic calculation. You find that the vertical velocity must not be 0. It's got to be big enough to fight the decay of the lid due to the thermal dissipation. And when you work out the numbers, you get rising motions of about 1 meter per second. And to conserve mass, the descending motion on the outsides of the vortex are also about 1 meter per second. And they produce, by this adiabatic warming effect, the Santa Ana wind effect, a warm ring. So this vortex is characterized by a warm ring on inside of it, but it's an outer annulus, basically, of that. And it should be a few degrees warmer than the cold center. OK, so this then is why we think we can use this as a thermometer. There must be something giving this vortex as well as the red spot, it's red color. There must be some red chromophore there. That's never been exactly identified what it would be. Okay, some people have argued that, oh, somehow this new vortex has appeared red because some red chromophore might have been dredged out and suddenly appearing inside of it. That's difficult to do because outside of this vortex, you're very stably stratified. It would require vertical velocities of 100 meters per second, say, to bring a red chromophore, say, from 20 kilometers below this into this vortex. It's very difficult to imagine that there's dredging of new chromophores in here. How would they appear? Worse than that, if I put in any red chromophore, even though I don't know what it is, most people agree it's some sort of solid particulate. If I put in any solid particulates in here, from nanoscale size to microns to tennis balls to basketballs, this meter per second velocity in the upward, outward, downward, inward motion, the secondary circulation, would fill this entire vortex within a month of completely uniform red tennis balls. You wouldn't see a red ring, and it would have turned red right after its formation. Instead, the red is confined to a ring, and it appeared one thermal time scale after. Well, our explanation for that really comes from some work by Bob West several years ago. He argued that the cloud layer on Jupiter is like a cloud chamber. It's at a critical pressure and temperature ready for gaseous ammonia to condense into solids and for that solids to sublimate as well. That's because you're at that critical pressure and temperature, that's why the clouds form. So he, for years, has seen people have reported very subtle hue changes, color changes on Jupiter. His argument is that the red chromophore particles, whatever they are everywhere throughout the entire weather layer of Jupiter. You don't see them as red because they're mantled in ice, bright, white, reflective ammonia ice, and so you mostly see white clouds. And the very subtle temperature changes could sublimate that, and you'd see the red chromophore. So this picture works completely well then with our thermometer here. Our picture is the following, that prior to a global warming of the planet by a few degrees, this oval appeared entirely white. The chromophores were everywhere, but mantled by white reflective ammonia ice, so the entire vortex appeared as a white elliptical object. Okay, now imagine, we're right at that critical temperature where we're going to start sublimating ice. If we raise up the temperature everywhere, remember what I said was the anomalous temperature, the temperatures inside, say, the ring and outside, or between the ring and the core, they remain the same before and after the color change. If there's a rising tide of temperature that's going to lift everybody's boats, the first part of this that would poke through and become warm enough to start really sublimating a lot of ice would be the red ring, and suddenly you see the red ring appear. Okay, so that is our explanation of why you get a red ring, why it's confined to a red ring. You can somewhat check this by now that you know that there's a red ring there. You can go and look back through old Hubble Space Telescope pictures. If this was really the process of a gradual warming, you should have seen that in the past, the less and less area of this red annulus would be above that critical temperature for sublimation. So you'd see a ring, but it would be thinner. Well, if you go back to before December 2005, when the red ring was identified, and you look carefully at the Hubble Space Telescope pictures, indeed you see signs of that red ring, and indeed it was thinner. So we see this object here as a thermometer, because we can't land any on the atmosphere there, a thermometer of temperature change, of global, not local temperature change on the planet, and that's why the red ring appeared. If this is true, we can start going back and looking at some of these other phenomena of these big incursions of color, of these big phenomena that happen at the equator, and see what is the explanation for those. If we find any explanation, is it dependent upon temperature or not? So I'll leave things there, but I think Jupiter's going to still unfold with a lot more surprises in the next few years.
So it looks like we had some time for a quick question or two. Any questions?
Yeah.
Yes. So you made the statement that if you had a couple of cyclones, you're able to mix feed very efficiently.
Pardon me?
So you made the statement that you have more than
Right.
one.
If you've got these a row of oscillating vortices, and they're chaotically oscillating, right, you can just do the calculation and show that it wipes out temperature gradients in the north-south direction. It's not a subtle process at all.
So how should I think about that on Earth, where you have more than one cyclones and we have a strong gradient?
Okay, on Earth, it's different from Jupiter for a variety of reasons. First of all, you don't typically get these nice rows of anticyclones happily, chaotically moving back and forth. Earth would be a much more, okay, don't quote me on this. Earth would be a much more interesting place if there were no land masses, right? Land, mountains, screw up, that's what's responsible for our local weather patterns. If we were like Jupiter, all fluid all the time, and maybe we had oceans and atmosphere, we would see a very probably different sort of weather, a very different kind of climate. So Earth's distribution north-south of heat and things like that is very different. What mostly takes the hot equatorial stuff and gets it northward, in fact, is not sensible heat, but insensible heat. You basically produce water vapor coming off the ocean like crazy at the equatorial regions. Storms then migrate north and take that water vapor with them, condense out, release the heat. That's the primary transport mechanism for heat. And it's a different business because of the very strong mesoscale actions happening due to the land. Yeah.
So I just wanted to ask. I wanted to ask you, how much of this has been confirmed with remote sensing? For example, I would assume that you could check your temperature gradients using, infrared remote sensing. You could check using lines for the presence of ammonia.
We would love to do remote sensing and have a direct confirmation or blowout of this whole theory. But if you look at the spectrum of Jupiter, there's nothing in terms of either emission or absorption lines that are smoking guns to tell you what the average temperature is. So for the Voyager stuff, which had an array of instruments on it as it went by, so that you get the infrared, there's enough information so that you can take a radiative transfer model and say, I'm going to fit these parameters and figure out what the temperature is. No flyby since then has had enough instruments to be able to do that. We would love to. I mean, people are trying now very hard. Believe me, I have my critics out there, and they're trying very hard. Typically speaking, I mean, the level where these clouds are is about 600 millibar. That's really where you want to measure the temperature. They're getting the temperatures at 100 millibar above and above. They're now trying to get down to 400, and I wish them luck. I mean, I'd love to see it, but that's the problem. We don't have a direct confirmation. I mean, but that's what we'd like to have, absolutely.
So you use the red color for one of the cyclones to show that there was heating locally. But then you can you again say why you can use it as a global thermometer?
Because basically, we said that the vortex had this warm ring and cool core structure. So the red ring was both warmer than the core and this outside medium. Okay, so the idea was before these vortices sort of, when they appeared white, the temperature everywhere, the chromophores were everywhere, and the temperature outside in the core and in the ring were all below the critical temperature that you needed to get sublimation. So the red chromophores, which wanted to peek through, were covered by white ice. Okay, so then imagine then that the constraints we have on this from our observations are that the vortex, its velocities and size and areas didn't change, that the relative temperature and pressure differences everywhere compared with the outside temperature, pressure, density didn't change at all. So they're the constraints. So now the question is, how do you make that red ring red? Okay, we know it's relatively the warmest spot there. So if I take the global temperature and let it rise, that means that because the anomalous ones stay the same, if I raise the average outside temperature outside the vortex by 4 degrees, it means I raise the red ring from what it was by 4 degrees and the core from what it was by 4 degrees. Everybody's been raised by 4 degrees. If now as you start raising things up, right, there's a critical temperature there to get to get the sublimation, okay, the first thing that's going to poke through, and maybe the only thing that's going to poke through, is the warmest spot, which is the red ring. So that's why it's a global thermometer change, because the anomalies are the same. You look lost. Yeah, Zach.
Would you speculate why the temperature is rising?
Right. I think the temperature is rising because Jupiter is absorbing heat at the equator because, right, we've got a more direct line sight to the sun. It's absorbing it above the convective zone, which would mix it meridionally. It's absorbing it in the weather layer, which has to be insulated from the convective zone. Otherwise, the vortices, these two-dimensional vortices, would never survive. All right. Observations show that something is transporting the heat between the poles and the equator, okay, or the equator and the poles, okay. It can't be convection. No one else has come up with a mechanism. Certainly chaotic motion in the vortices can do it. That may or may not be. We certainly have shown that it can do it. If nobody else has an explanation, then that's what we've got as our working model of what's transporting heat between the equator and the poles. If we cut off that mechanism, we needed this row of vortices to be happily oscillating back and forth. If we cut off the chaos by reducing it to one anticyclone and cyclone, then we now have a barrier to transport at 34 degrees south latitude. You're heating above that between the equator and there. You're going to heat it up. You're going to cool things down. You should see the equatorial regions rise and the polar regions cool. That's the basic idea. We can't prove that these are the only, right? What I've shown in all of this, the red coloring, the heating, the transport, I said, here is a mechanism that we know by simulation and back then we'll do it. We cannot prove it's the only one. Please, somebody come up with an alternative explanation, right? Anybody in this room can do that. Yeah.
You talked about the equator rising and the poles falling, but that would change the rotation rate.
No, I'm talking about the temperature.
Sure. But I mean, if you increase the temperature, you increase the scale height.
This is an nth order. I think that's a very small order. I don't think we're going to change the rotation. I think that's a very small effect. I mean, there are other effects that I haven't mentioned that are going to come in. For example, if the clouds want to form at the critical temperature and pressure, then eventually the level of the elevation of the cloud deck will change. Also, the vortices are at their particular height because that's where they accumulated small vortices to make big vortices. And that process could change because, again, probably the small vortices are due to that nuclear testing effect that you get ageostrophic weather plumes coming up. We can see convective plumes there. When they hit the tropopause, when they're very stratified, they said, oop, I can't go up anymore. I move outward. Right? That positive horizontal divergence of the velocity in a rotating system produces anticyclones. That's the exact same effect, but much bigger than in a rotating planet. You let water go down the drain, you get a negative divergence. You produce a vortex in your sink. Right? Same effect. So undoubtedly, the thermal elevations, they're going to determine where the vortices are. So everybody's going to start shifting around. My hope is, not my hope, one scenario that I've thought about is that I think, as I say, these jet streams are not all that stable to baroclinic instabilities. The three white ovals, we saw them form in the 30s. Before the 30s, we saw a row of vortices. Not very well because our telescopes weren't great. But we saw a row of vortices. Then there was a disturbance, some big, huge wavy pattern that lasted several years. And then suddenly these big three vortices appeared from that. My guess is we're not at a special place in time in the universe. This is a cycle that happens over and over again on Jupiter. This particular cycle is probably about 70 years long. Right? What happens is, right, these guys will become paraclinically unstable. The jets will produce waves. The waves will produce new vortices. They'll start transporting heat. You relax back to where you were for many years. But as you're going back and forth, and we've done this also, as these vortices get close to each other, they tend to erode each other. And you're going to get those cyclones below the critical strength where they suddenly fall into the troughs, and the cycle repeats. So I'm a favor of cycles, not one-time changes. Right? You have to be very, very lucky to see a one-time change. So I think this whole thing is a cyclic process. I mean, we certainly see now, by the way, on the other giant gaseous planets that things are not steady by any means. So When Voyager went by Neptune in 1989, it reported on the great dark spot of Neptune, which was its key and important feature. So you've got Frank Shu's book on astrophysical gas dynamics. The cover is a picture of Neptune with the great dark spot. Well, it's no longer there. It was an ephemeral object. There's cycles happening on the weather of other planets. I think we have to deal with it.
Second edition.
Absolutely, absolutely. We better eat lunch.
With that, let's thank the speaker, Phil Marcus, one more time.